My, the time flies by. Let me review where we left off. Last 3 lectures, we started by saying, there sure will be cycles. The Earth is turning. Sines and cosines do the job. Exponentials combine them. We wrote down an interval discrete representation of summing a bunch of sines. That ended up then in an analysis, continuous time, discrete frequency, case A. I haven't written the following word, which in retrospect I should write, and that is the sort of the moniker harmonic analysis. You will find people writing entire textbooks about it. You will see that we're transitioning sort of out of there into the more statistical analysis of the cyclicities and so on. It's a subtle point at some point. But anyway, I want you to have the word in your mind. Harmonic analysis. Obviously, harmony is all about making sure that your strings, which are finite intervals, are properly tuned. I didn't talk about beating, but you know, if you combine 2 closely spaced frequencies, that you get a beat pattern, and that there is a new oscillation that develops. There's a group velocity, there's a phase velocity, there is the difference in the average of these frequencies. All of that stuff that you learn in physics is obviously coming here. Anyway, we then went and made that unit interval some finite length. That wasn't 1. That's just the normalization of the frequency. Then we wrote the first important transform, which is a Fourier integral, okay? A transform which you need to remember, understand, and look at, and realize it's ultimately very easy. None of this shows you that it needs to be true. The only thing that it shows you that you can write it, okay? The motivation that this is true and possible for every signal, that's sort of space analysis of the Hilbert space and the L2 and so on. Here we just write these things. Infinity, continuous variable, integrate over your dummy f here and your dummy t here, change the signs, and so you have an orthonormal transform pair. You look it up in books, people will sometimes put prefactors, they will sometimes write 2 pi f as omega, they will sometimes write a prefactor in one or the other. None of that matters, or rather, all of that matters very much, and it's very annoying, but it's only ever this what they mean. Then we're sampling, and we get a new transform pair with a new so-called Fourier transform of the sampled signal, P, and this P ended up being periodic. Then we looked at, all right, if it's periodic, it's just repeating stuff. What does it have in the non-repeating interval, or rather in the generating interval, which ends up between the interval between negative 1 over 2 delta t and plus 1 over 2 times delta t. So that's the central interval from which we repeat by going out to the right and to the left. We did a minor amount of mathematics, only involving a trick of summation, and we discovered that which is periodically repeated, that part of the Fourier transform of a sampled time signal as a function of frequency takes stuff from the real Fourier transform, the B transform, the one that I said was true, and repeats that. And what does it take? Well, it aliases pieces from the frequencies that it doesn't provide independent information about, but rather at which it states these copies. And what does it take? Well, that stuff that's from the inside this interval contains contributions of the true Fourier transform of the true signal, which is red, and hatched slanting to the right. And then it pulls in the stuff from all sides, okay? And therefore, all of that power, which really belongs to the other frequencies, is now inside that interval, and then that's being repeated. And so that is aliasing. And then we notice simply how, well, you make these things match if there is nothing outside a certain interval. If there is nothing to alias, you're not going to have this problem. Which then says, well, now turn the problem around. If you target a certain bandwidth that you want to understand, sample it such that this thing matches. And then I went to, let's just write that formally as, there will be a band limited signal. It will exist. I will want to know it. How can I know all the information about it without aliasing, without any leakage, without any bias? Aliases are a form of leakage of the term, and it's a bias because it's no longer the truth, but it is misled consistently. How can you know everything without bias, without leakage, without any loss of information, without any aliasing? Well, take your bandwidth where your signal lives, sample it at the delta t that is attuned to it, and then you do not get this bias. But then you're saying, well, wait a minute, you're telling me that a band limited signal, which is continuous in time, I only really need to know at these samples delta t. And then I say, yes. Have you been listening? Exactly right. You only do need to know that signal only at those delta t's. And then you're saying, but what if I want to know in between the delta t's where I've taken samples because I want to make a pretty picture, or I want to sort of fill in the looks of it for God knows what reason? No actual God involved. And then we say, well, if we write the simple consequence of what we've been doing, then you can reconstruct the continuous signal, the signal of the continuous variable t, from its samples, which are the dots taken along its course, because you can reinterpolate them using this thing, which ends up being a cardinal sine or sinc function, which is just a sinc of pi x over pi x, the argument. And note that some people don't have the pi in there. All right, so that is probably the most fundamental theorem of this sort of duality of, having an objective reality, which is of course continues in nature, and then you being a scientist or an engineer and you taking samples and then you realizing I'm repeating information that shouldn't have even been there, but wait a minute, I can actually do it right if I do it. And what if I do it right? Then I get this Shannon theorem interpolation way of doing things. And so that is called the sampling theorem, which underpins almost everything else. 1/2 delta t is the Nyquist frequency. Note that can be both positive and negative. We've always done the interval plus and minus of 0. The sampling at delta t, if it is matched to this w here, that's the Nyquist rate. And I'm also warning you, don't get confused. Some people write this as plus and minus w over t, and then you get different expressions. There are many ways that you could take a paper or a textbook and be off by a factor of 2 in this business, a factor of 2 pi, a factor of a square root of 2 pi. Those are the main ones. So the Nyquist rate is the rate at which you need to sample a signal in order to know something about it, no more and no less. And then I gave you my picture of saying, imagine some wiggles, and it stands to reason that you'd be needing to sample some sinusoid twice per period, and actually epsilon more than that, such that you can completely reconstruct that signal without any aliasing. And so that picture didn't come out so well. It was a little late, and tried to say, imagine sampling an infinite sinusoid once. You will never know it's a sinusoid, obviously. Twice, well, it depends how closely you're spacing it. So delta t apart, make sure you hit it multiple times per wavelength, and then you will have none of that aliasing, because if you're right where you're at, where you were, where you want to be, you get that frequency with the proper information. And then that was this picture here, which imagines you're inside or you're outside. And so you want to be inside when you want this thing. So this is very important, right? If you're in geology and you drill a core and you want to know something about, the cyclical nature of time and orbital variations or climate series or whatever, and you know that the Earth turns and there is that obliquity, precession, eccentricity, and that's 18,000 years or 23,000 or 100,000 years. If you know your sedimentation rate or your snow rate, if it's an ice core, that sort of dictates how finely you need to sample to get those sorts of oscillations without any aliasing. If you are sending a satellite around the globe and you're trying to measure the Earth's gravity field, which we do all the time, and you want to loop around the globe and you want to say something about how the Earth's gravity changes with time, which we do all the time, don't be looking at frequencies where adjust your sampling rate such that you may or may not get the tidal cycle or whatever period of observation you want. So that all goes into the design of your experiment as a scientist, but it begins by understanding on a theoretical level what happens if you sample a periodic or infinite or band limited signal and what sort of inference you can make out of it. Then I was pointing to all of these things again, and I said, watch this sink, okay? And I'm going to yellow the formula just because it's striking my fancy. By the way, for the geophysicists or astrophysicists out there, there is no sampling theorem for spherical harmonics. It doesn't exist because of the poles, obviously. There is no way in which you could put dots on the sphere and reconstruct the complete information without losing it. As opposed to here, in the plane and in time, there is a way in which you can throw dots at a line and have all the information about a band limit process. This is the way, and it helps you find what you aren't rendering by interpolation. And while I will not talk about it, I'm actually going to make a note here that compressed sensing, it is not, okay? This is for all of you out there who are going to encounter this field of signal analysis that came and stayed, in the last maybe decade or so, where people were writing papers saying beyond Nyquist and this and that. They were making 1 pixel cameras and all sorts of things that are completely counter any of this. So they basically killed Shannon. I'm just throwing it out here. That is a theory where people said, look, you can let go of this exact sampling that pertains to band limited signals if in some other sense the signal really only has few components in some other domain. And that's the notion of sparsity. And so those of you who stick with me are going to hear more about that elsewhere. But if you're sort of seeing this class as an entry into science or the literature, then you're going to end up here pretty soon because people have been talking about that a lot. It's trending. So then I was looking at this and I'm like, the sink is everywhere. What is the sink? No, it's a function. Should I draw it? I will draw it. I'm going to do a fairly poor job. So a sink, I can't draw it correctly. I'm just going to sketch it. Let me draw the sink squared. That's going to be actually more interesting now. It's wiggle, 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 big wiggle, 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 wiggle. Okay. I really am not going to give you a full discussion, but there is a notion of a central lobe and a side lobe. This literature is full of people discussing side lobes and side lobe reduction. It'll become clear in a few minutes. Here's that. I want to make you see, even though this page is getting very busy, that the sink was what I got when I integrate between two limits that are not infinity, a complex exponential. Tis another way of saying that the thing in the square brackets is the Fourier transform of the function 1, but only between those two limits. That's, of course, another way of saying, now I'll sketch the function 1, but only between two limits. What is the function 1 only between two limits? Well, it's a little plug. Back in the day, engineers coining these terms, they called it a boxcar. I hear that that is an actual wagon of a train. Constant value, I'll call it 1 here, could be 1 over t. So again, a central lobe and no side lobes. So it turns out that by identifying the limited Fourier transform of the constant, that gives me a sink. I'm squaring it here because it is more fun for me and for you later. And so I told you that in this business, people will write to you a bunch of, you open a book and they'll say, here's these Fourier pairs because you're gonna wanna need them. Well, this is a common one. So they are each other's Fourier transforms. So the limited the limited frequency Fourier transform of the constant is a sink. All right, I told you all of this because I'm saying that I'm going to reconstruct a continuous time signal from the sampled time signal using sink interpolation. And I'm leading in with the answer. I'm going to say, well, that should be obvious because I'm about to show you that the Fourier transform, in order to get the Fourier transform of a convolution, I can multiply the Fourier transform of the function. Let me say that again. If I take a function f and I convolve it with g, and I ask what is the Fourier transform of the result, then I can also say it will be the multiplication of the Fourier transform of the individual pieces. Somehow this already needs to make sense that sampling within a delta t, remember that only really gave me information without aliasing within a certain limited frequency. So it's like I've cut the Fourier transform of a signal by multiplying it with a boxcar which selects that central band. That's how I recover the continuous version of the signal. And in the time domain, that's a convolution. All right, I realize that I've been talking with things that I see in my mind's eye that may not make sense to you, so it's time I write them down. But they're on the record now. So you remember convolution. I wrote it down numerous times. I also gave you some pleasant ways of thinking about it, digitally, by summation, by integration. We first encounter it as needing it when we describe the action of needing to formulate the PDF of a sum variable when we knew the PDFs of the individuals. This arises there right then and there. I'm just gonna give you this here now. So this convolution Fourier duality, okay, sometimes also called the convolution theorem, it exists by Bracewell's count. And Bracewell is an authority on the subject. I'm going to write this here because you'll encounter that book and then you'll wonder, is it a good book? Well, it's like a classic. There are 20 different versions of this. You can imagine there's continuous time, discrete frequency, discrete time, discrete frequency, and so on. So I'm just going to write you the one that I think is the best one for you. And that is the discrete time continuous frequency version of that. So let's have a signal f, some function f, and let's convolve it into the function h. And let's do it all discretely. So there is t dt. And remember, t is the index and delta t is the sampling interval. And cheating a little bit here, taking a look at this thing, which I wrote, right? So that obviously is a convolution. I'm going to write it properly and say t prime, which is my dummy, over which I sum and which disappears. That's most of the trickery in this mathematics. Yeah? Goes from negative to plus infinity. And so I'll have a signal f at delta t times the index t prime. And I'll have my h of my t, which I'll make red because it's the surviving t. It's the argument of the convolution, the argument of the result, delta t, minus the block T prime, delta T. And there does belong a delta T in here, which I write early. I usually like to write it late, but I would run out of the page. Why do I write it late? Because we're often in the business of converting things like integral of f of x dx into sum of f of x delta x, which is a procedure known as mental connection. I'm telling you how I look at these things, right? So first of all, I see the colors, even though I am colorblind, but the T is the argument. The T prime sums out over it. That needs to be in the sum. It needs to disappear. It's how you remember it. That is also the same notation we use for vector multiplication. You know, repeated indices, it sums out. That's Einstein's notation, blah, blah, blah. Keep going. But now I'm saying, you know, I write this delta T usually to the end of my sum, but I would run out of that page. And so the whole idea of having something like an fx dx being equal at some point to an fx delta x times a big delta x, which I therefore am writing. Well, and now I'm making a mental connection here that I want you to know the general word for replacing a sum with an integral.
Are we talking about linearization?
It does enter into it. Name of a person as the type of summation, and name of the procedure, which you will need to know if you're doing numerical work, discretizing integrals and doing them.
Is it Riemann?
Yes. So Riemann is this name of the, you know, summation type. I want to connect this to the general field of numerical integration, and by another name that I just find interesting. That's called quadrature. Have you heard this term before, quadrature? Yeah, if you have, good. If you don't, well, you now have. You wouldn't look, I find this an interesting word. Why is it called quadrature? Any thoughts? Have you ever heard about squaring the circle? It's called quadrature because for ages, right, people have tried to find the area of a circle as a square of something non-irrational. So quadrature of the circle is numerical integration. Squaring the circle is what the English version of that is. And pi makes this impossible. But enough about that. So now I'm going to write the Fourier transform of the f's individually. So there's an f wiggle. And now, you know, it's just a little sad. I need f for frequency. How about I like change my font a little bit? Now they're like this, because I already have an f. Okay, so now I'm just looking up which Fourier transform I should be looking at. Well, obviously, I need the discrete time continuous transform. So I'd be having, now I'll just write it in a single t of this time domain version to delta t of the e to the negative 2 pi my little f here, which is weirdly looking, my TDT in the exponent and my delta t. Okay. And just because I'm a conscientious person, I go back to the note, right? So I'm writing D, transform previously called D. So then you write the same for H. You have to write it here. It pays to write these things at least once. It takes time, but then you get practice. Infinite sum, dummy index, actual function in the time domain, sampled close brackets, minus 2 pi, frequency f, nothing to do with the function f. I should have called it g. Okay, I hope it was just me, but my whole system crashed again. I was just writing that, right? So I need maybe another symbol for the result here. So how about I call it, you know, mathcal f. So the convolution of f and h is this very fanciful f, and I want to find out, well, I have written it, and here's t delta t. So I'm just going to spare you the details. But if you've been listening, that you know you could do it yourself, as long as you remember that whenever you take sums inside, that you have your own indexing going on, that you know, that way you never get lost. And it doesn't take much time. But what you realize, I'm gonna write it right here. This is about as much space as it would take if you're writing it out. And I think you should write it out. It's a good practice. The result would be that the Fourier transform of this thing that I've just made at whatever frequency you're considering equals the Fourier transform multiplied times. So that's the main result. That's the convolution theorem. I write it discretely. You can do it this way by filling in this blank. You'll look it up in a book. They'll do it continuous or this or that. There's all these different versions. It's what you definitely do need to remember, that convolution and multiplication as operations are each other's Fourier pairs. And I could say so many more interesting trivial tidbits about that. Whenever you multiply by hand on a piece of paper, you are convolving. Whenever your computer multiplies, it really is convolving. However, when it is really convolving, it often is doing it via Fourier transformation, because Fourier transformation has become so efficient, which is another story. But so it's a really, really, really central theorem. So convolution, multiplication, Fourier pairs. So now with that, this is a proof, right? And it's simple. I want you to go back one final time to that Shannon-Whittaker formula and follow my thought again. Maybe I'll draw it. You have a continuous time signal. That's your science. That's the thing you want to know in your engineering. It doesn't need to be not, it only needs to be, you know, square integral. As it is. That's your objectivity. That's your truth. That's your thing that you want to know. But you can't get it because you live in the real world. So you sample it. You're doing science. And I'm saying sample with delta t and recall it index. That's called abusive notation at this point. Right? So here's frequency. And here's frequency. I'll draw a 0. Again, I'm hand sketching here. If I properly sketched, I'd watch my symmetries and my this and that, because there's a lot of Fourier theory that tells you how to guess at the Fourier transform or something. I'm not implying any of that. I'm just implying that the signal that I want to know has a Fourier transform. How about I draw it in its squared form, like I did before? Just because I wouldn't have to draw real parts and imaginary parts and so on. So blah, 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 blah. Here is the Fourier transform squared of the signal. And it goes through anywhere, right? Because the truth knows no bounds. Temperature exists. Time series happen. Then you come in with your science and your whatever test tube. Or rather, what am I drawing here? It is not a test tube. 10 points for whoever knows the word for that. Distant cousin of Riemann.
Erlenmeyer.
Thank you. Excellent job. That's you sciencing, sampling, as good as it gets, and it's even, and it's, you know, what we just discussing. But oh, what have you done, right? You have now periodized your transform, and not just that, it's no longer the good one. Sketch again. The original true background that you want to know, which I now draw in pencil, is now suddenly becoming something else. In the interval 1 over t delta t plus 2 delta t, it has changed. It is different from the truth because of aliasing, and it's been periodized. It means it's going on. And where it is going on is muchly different from the truth. Because, you know, I'm now literally trying to sketch a semi-realistic signal situation for a signal where, you know, this is what there is, and you're sampling somewhat reasonably. And so where you expect to get to know things, you're doing an okay job, although there is that leakage due to aliasing, which gives you a bias. But then in that periodized portion, where you previously only had tails, now you have like a whole lot of stuff that weren't even there. So clearly you don't want that. So now I'm saying I need a way to think about what I'm learning about my signal as a continuous time. I somehow need to reconstruct it. And I've been teaching you that if I use my buddies Shannon and Whittaker, that by convolving with the sync kernel, that's the convolution kernel. Well, it happened again, and I still don't know why. I cut off, obviously, and I'm back. Let's hope to get through a little bit more of this. So, truth, science samples, true spectrum, periodize and alias. We're trying to reconstruct a signal from its samples to do inference. If we have a periodized and aliased thing going on here, then of course we're going to get a wrong result. That's my way of saying S hat of t would be an estimate. Remember, I tried to know about this by doing science to get to a conclusion in the usual ways, and even with the same notation as before. And I'll just draw it somehow, making it look wrong. My inference is bad because, you know, I got that aliasing going on and that periodization. So why is that different from the truth when I convolve with this sampling function? Well, I'm going to draw this in the frequency domain. It's because when I sit there, now I'm going to draw something I haven't drawn before, which is the Fourier transform of S hat, S wiggle hat squared. So truth, science, inference, prediction, etc. What sort of thing am I going to draw schematically here? What is the result in the Fourier domain of having convolved with the sync? Tell me schematically what the nature of my picture is going to be.
I think it's just between the Nyquist frequencies, just between -2 delta t and +1/2 delta t. Because if we use the sync function when we do Fourier transform, we get the boxcar.
So exactly, that is what that is. So if I do what I'm doing, then I'm literally just chopping off the tails of my periodized transform by multiplying with a boxcar. And so the boxcar chops off the tails again and allows me to do a reconstruction. Of course, it's still wrong because it's aliased, okay? But bringing it all together, if you started from a band limited function, in other words, one with that support, also technical term, the support between 1/2 and -1/2 signal, then the effects of periodization in the frequency domain would be undone, and there wouldn't have been any aliasing. So it's a bit of a long way around here to make the same point, but I think it is useful to see this, to keep this picture in mind. And many of you will work in the time domain and know stuff and do regressions and whatnot. Many of you will work in the frequency domain. Many of you working in the time domain probably should go to the frequency domain now and then. Many of you working in the frequency domain really should go in the time domain when they can at some point. And it's all not the same, but it's all related. And there is very little else going on in this field other than the convolution theorem and the sampling theorem, and knowing how to integrate a bunch of exponentials and not losing anything in indices or multiplications, and sort of keeping track of things. And then finally, if I summarize this whole field, it is also about, well, being patient with symbols and stuff, because sums of squares and squares of sums of squares, it just ends up being a lot of writing. But this picture is meant to show that if you sample right, you get the right inference. You're gonna start knowing things. And I want you to see the hats on there as our estimate. So now I want you to think about, well, look, all the usual connections apply, all the usual questions apply, right? This page here has been about S hat as an estimate for S. Well, estimating S as S hat. This is not rolling off the tongue. S hat is an estimate for S, which means that whatever we do in time series, we need to ask our same questions of what is the bias of that? What is the variance of that? And so on. So Terry, earlier you said, it's going to be a noisy version, because I didn't draw it very well on the left here. But I haven't talked about noise per se. There is nothing here yet, ultimately, that is properly statistics, because all the variables, I've said there is an S. It has a Fourier transform. I have sampled it. The Fourier transform is a deterministic operation. You just take an exponential, you multiply, you're done. But now I'm bringing this in, and that's going to be for the next lecture here, where I'm saying you got to start thinking about it statistically. You have to start thinking about a sample that not only is not everywhere and is therefore on a grid, but it's also making this measurement perhaps noisily, where your hand will shake every time you take somebody's length in your doctor's office. And what do you know then? Then you get the effects of sampling and discretization, and you get the effect of noise. But in order to do that effectively, we need to talk about statistics statistically. Okay. When I say bias on this page and today, I've sort of loosely said this is the stuff that comes in from the edges due to aliasing, that the bias is the result, because you can't undo it, right? On page 70, I'm going to treat the treatment of periodic signals statistically, and we're going to be more specifically no longer consider having a truth, having a signal like I just did today, but we go back to our statistical viewpoint and say, well, that thing is itself drawn from a distribution, and we'll write a representation that is stochastic. That's just a fancy word for having many moving parts in a sort of a statistical way. So we'll have a stochastic representation that is spectral. I'm just throwing the words here. And if previously in lecture 1, I would have said to you, my body temperature exists. I consider it a random variable. I make a noisy measurement. Then I treat what I can know about my body temperature in that sense. Then I went, I defined my variable of interest as a power spectral density exists. Then in the second half of this course, we're like, a trend exists. I want to know it. Here, our representation for the last concluding one will be, there is a power spectral density, and I want to know it. And so I'm then going to bring back the notions of bias and variance that I raised here before. So I know it's time, but I cut off and I wanted to save page 70 for the thing that you also do still need. And maybe I'll just write the title and then I'll take a poll if I can extend it here. What we haven't done before is we haven't done the actual work of finally writing the discrete time, discrete frequency Fourier transform, even though you can clearly guess that that's going to be the important one because you're a scientist and you're sampling and then you want to know stuff and you're not sitting there integrating anything by hand, you're computing these things. So how can you get discrete frequencies even though your signal is continuous, but you've been sampling it, and in principle it stretches to infinity, but you can only get so much of it. So all of the practicalities of having a finite observation window, an inherently discretized way of taking samples, and then only computational means to evaluate the transforms, that brings us to a discrete time, discrete frequency transform. And its algorithm, often used, most popular, but by no means necessary. And what is the most popular algorithm to do the discrete time, discrete frequency transform? Just throw something out.
SFT?
Yes. And the F stands for fast. But that's just an algorithm. That isn't a thing. This is the thing. DTDF, that's the Fourier transform that we're considering. Okay, I have a plan. I understand that some of you need to go. I do want to throw this page full with the discrete time, discrete Fourier transform. So if you need to go, please watch the last 10 minutes of this thing, which will be recorded anyway. And if any of you have any problem with that, let me know, and then I'll just take it on Tuesday and I'll just make sure I go over that again. Okay, it's not that much. I'm going to fill this page for the record. Same picture as before, needs to go in your mind, right? Continuous signal, sampled, and now I need to have some way of dealing with the computation that will give me power at frequencies, knowing that I can't get them all because I'm on a computer and I need to stop at some point. So this will need to relate sampled in time to somehow sampled in frequency. And you can already see that there's clearly complications because, you know, we haven't done that before. If I condense this down to the 10 minutes that I think I should be devoting to it in the interest of time, I would say here's the most important thing. Well, there will be frequencies. I'm on a computer. They're now indexed. Let me begin by saying I have a time domain signal, but of course it's sampled. And now I'm counting the first, the second, the third, the fourth sample. Okay, so let's say I have n samples. I'm going to make it as realistic as I can. The complications can wait till later. I only have n samples. The best thing to do is to pick n frequencies. So I'll call it sample I is 1 to n, or 0 to n minus 1. So I'm saying I'm going to need to compute the frequencies, and it's continuous, right? Because everything we've been doing. But I'm like, you know, you got to pick something because you're on a computer, so you grid it. I spare you the long discussion, and I say, pick n frequencies to compute the DT, the discrete Fourier transform of this sample signal. N time samples, n frequencies. That just specifies the number. You know that the Fourier transform is going to be periodic, because it's a sampled signal, and I just went through that. So it doesn't really know, it doesn't really care where you label it. You start out with 0, keep counting. You start at -1,000,000, you know, it's just offsetting, right? It's all periodic. We already know that. I, however, do like to keep 0 frequency in the center. So now is a practical way for you to do things. Why? Because 0 is, remember, that's our mean. That's our DC term. That's our 1-degree polynomial regression. A 0-degree, rather, 1-term equation, 0-degree polynomial regression, right? The 0th frequency. And I'm making this point, nobody tells you have to pick 0 as a frequency. You could pick 0.1 over pi, and then you just start counting. So I'm just giving you a way to count. What you do know, though, is that you also need to stop somewhere. And you know that you're cyclical and that you have nothing to expect from going beyond the confines of a Nyquist frequency, 1/2 delta t, and -1/2 delta t. So I'm saying pick n frequencies on this axis. And then you are going to say, yes, but that means I need to choose where I possibly reach my Nyquist exactly, because if it's even or odd, I cannot ask to hit both boundaries and 0, so I got to decide. I'm looking up what I decided in my own codes because I can't remember. I hit it on the right. I'm schematically saying you're going to get information about this frequency and this frequency and this frequency and this frequency and so on. I'm just drawing them all as dots. I definitely want to hit 0. And then if I have an, what is it, even number of points, I will hit the Nyquist if I can. Sorry, I always hit the Nyquist on the right, but I'll only hit it on the left if I can. The negative Nyquist. Okay. I need to tell you these things because when you're using the algorithm FFT, including the MATLAB, it doesn't tell you what the frequencies are. It doesn't care. It just says, here's the first, here's the second, here's the third. You then need to tell it what your signal is like in order for you to make sense of what the frequencies are. This is a very important point. And I'm saying you got to make your own frequency axis. And I recommend that you make it go through 0 and that you hit the Nyquist on the right. And then if you can, because you have an extra point, you also hit it on the left, but not always. That's because n can be odd or even. Okay. Now, the spacing in frequency is 1/delta t divided by n. I'll call that delta frequency because I divide 1/delta t interval into n pieces. That's the spacing. That is 1/the duration of the signal. And that makes sense because what that means is that the first frequency that you can recover is this beyond the 0 frequency, which is the mean of the signal. If I have a signal of length t, I'm just mixing notation, or rather I'm adding notation here. If this thing here in time is of length big T, then the first frequency that you get is 1/n delta t, which is of course 1/big T. That's the duration. And that must make sense. Why does that make sense? Because you got to imagine some really long oscillation of length t. And when you have done this sampling, then regardless of the sampling in a way, but only depending on the duration, it stands to reason that you cannot really get much more information about what happens at times before this length of time and after this length of time, right? If I look for oscillations and I only investigate a minute of time, I will not have any information about a potential 3-minute signal if I only sample it this way. This is not quite exactly mathematically properly said here, but it's heuristic. is motivational. If you're interested in a 100-year cycle, don't just measure for 99 years. And on the other hand, the shortest period, of course, is the Nyquist, because that's 1 over 2 delta t. That's the shortest one, right? That's what we talked about. So 1 over 2 delta t is the frequency corresponding to the length of that. So that actually is 2 delta t. That's the shortest time cycle that you can get. And the longest time cycle that you can get is big T, which is n times delta t. All right. So that's the Nyquist frequency, the Nyquist wavelength at this Nyquist sampling. And this 1 over t also has a name, which is not Nyquist, which incidentally should be Nyquist. Some people call this the Rayleigh frequency for reasons we can get into never, unless you can see. So there's that, there's that. So then I want to have you wonder, what about a real signal? How could I turn n time samples with the real valued numbers into n frequency samples, which have a real part and an imaginary part, which means that you really have created 2 n values. That simply is impossible, right? You have no way of using a unitary transform and making up information and somehow turning n numbers into 2n numbers without repeating yourself. And that is exactly what happens. If you ask for n frequency samples, your return is symmetric. Your Fourier transform that you're going to get in this discrete sense is symmetric, which, again, if you do the continuous theory, people will crank through exercises saying, take this, take that, even, odd, you know, symmetry, this and that, and it's just tedious. So I make this argument. You do a discrete Fourier transform, you give it n numbers, you need to have n pieces of information. If you're asking for n between negative and positive 1 over delta t, you're getting a real and a complex value. That's really 2 numbers. Then I'm saying you will look at that and you realize that there's what's called Hermitian symmetry. I'm name dropping like crazy today. And then I'm saying you could take a look at that, and do take a look at that. But all that means is that we really only need half of them. So what half are you going to take? Well, you can take any half of them, or any interval of length half, 1 over delta t of them. But it makes most sense, doesn't it, to take this half, which starts at 0 and ends in that Nyquist frequency that you always hit. And now I remember, that's why I hit it on the right. Okay, so you will want a discrete Fourier transform that's going to give you all of these numbers. And if it's a real signal, you will throw half of them away because the other ones are mirrored, let's call it that way. Which half to throw away? Well, I'll take this middle to the end half as a keeper. And then you do need to realize that however MATLAB gives it to you, there's a thing called FFT shift. I'm just throwing it out there as a function here, because I am not telling you how MATLAB's algorithm, if you're using MATLAB, actually orders these frequencies. But again, it's periodic. It doesn't matter, but you do have to figure it out. And so here I'm saying, all right, conceptually, I take this half of it, which means that I can capture my signal, represent my signal, my n numbers in the time domain, which is an ordered time sequence, by an ordered frequency sequence. And that if I wanted to compute myself a little axis to plot it at, I would say begin at 0, end at 1 over delta t, go in n over half steps, put the right amount of floor or ceiling rounding in so that you get exactly these frequencies like I'm drawing. And then the first frequency will be the mean of the signal, which if you've demeaned it to begin with is going to be really, really, really low. So if you plot a log 10 of that, it's going to be negative 30. Don't even look at that. That's not interesting. But the first frequency is going to give you, starting to give you information about the length, the duration of oscillations, the duration of your sample sequence. The last one is going to give you the shortest amount of wavelength information that you could possibly recover. And next lecture, we'll talk about the fact that it's really the variance of these terms that's important, and the square of it. So we talk about power and power spectral density. But I feel like I now can conclude by writing the form of the transform And then really signing off for the record. So D prime, now we're on E. That's the last transform that we will want. That is, what is that actual transform looking like? So I'm going to define it as follows. My sampled signal is ST delta T. And now I'm writing a particular form. It is this for a dummy variable little n, which counts the samples, and which is going to give me my Fourier samples, and it's going to index them with that n. So in a way, I could talk about this is FDF, but I think that would just confuse you and me. So knowing that my result is discrete, I just index it. All right. So now I write my negative or positive exponential, e to the I2 pi. So far, so good. There definitely is a T delta T. And I write it like this to bring out some more structure here. I'll do little n over big N. And so that's supposed to make sense, just like before. Delta T over delta T doesn't matter, right? So little n over n is how many indices I am into my total number of things that I have to index. Just like very, very early on, I'm like, that's like the fractional thing that I'm into the cycle. So that counts to T2 pi. That's just in sample space, n over n. Of course, in real space, I have an actual time. So I bring the time in here as follows. Then I'm going to write what that thing is. That is the Fourier transform. And I say that now better be delta t. And actually, you know what? I'm going to say our t, which was always an index. Let's really formally make it an index so nobody's ever confused. S sub t. So at delta t, I have my index little t. And it too goes from 0 to n minus 1. And what does it take? It takes my s of t's and my negative I2 pi exponential. And then I might write that this way. Bottom line, it's the same thing, but I make it a little bit more interesting by having you think about, well, for whatever n it is, it's like I'm looking at the oscillations. There's a complete symmetry that I see here. So instead of writing nt divided by n, I wrote n over n times t, and here I write n over n times t over t. Just a little typography going on. Every time I multiply and divide by a delta t, just to show you that it doesn't need to be there, but I do like to think about it because I was thinking about the t delta t's, and I've written myself a new transform. And then you should be asking the question, well, all right, okay, take a look at that. You got to reflect a little bit on that. I'm now making two final comments, literally the last one. FFT algorithms do this in some form or another, and you do have to check what their definitions are, because sometimes they do this, sometimes they do that. They don't always do the same thing. There is a choice at how you divide this normalization factor. The FFT algorithm doesn't know about your delta t, so that's not going to be in there. So you have to think about that, but not very much, which should be obvious what you get out. So that's why the FFT is an algorithm. It's not the thing you want to do. It's the thing that does what you want to do. And if you need to verify that this actually is a pair, then I would say you might want to need one final thing, and that is considering the orthogonality of exponential sequences. Remember, I started with orthogonality of sines and cosines by integrating, of exponentials by integrating. We haven't written a sequenced orthogonality yet until now. And so I'll just write, because I know you might need that, the sum of n to n minus 1 of e to the I2 pi of n over n of an integer z, which arises when you multiply these things together, is big N. Okay, so I'm just throwing that out here because if you are tempted to multiply these things together, you will encounter this. The sequence form, this sequence here, and how it sums allows you to use orthogonality to prove that this is a pair. Okay, so this is, I think, where I better end. We've done Fourier series, Fourier integral transforms. We looked at what happened when we sampled in the frequency domain and time domain. We rediscovered yet another convolution we needed and how it related to multiplication. And I wanted to make sense of that, and I hope it all does make sense. And then we ended up with what we really do, which is to compute Fourier transforms as discrete sequences, because that's how computers do. It's not continuous. And then you set up this pair, and then you implement that with an FFT, which is an algorithm, but again, you don't need to use it. In fact, MATLAB used to have another algorithm in there called DFT, but they made it disappear for some dumb reason. And then if you're giving yourself 1, 2, 3, 4, 5, 6, and you're asking MATLAB, what is the FFT of that? It's going to give you a result. And then you need to tell it that, hey, by the way, that was 3 hours of data. That implies a delta t of 3 divided by this many minus 1. And so you give it a delta t spacing. And then only can you know what frequencies you're looking at, because then you have made yourself a delta f spacing in that way. And I sort of sketched this way because if you start writing it mathematically, it makes a lot less sense. And there's so many choices and it takes a long while. But so go ahead, check MATLAB's FFT algorithm. Check how it relates to the pair I'm drawing. I also regrettably inform you that there was a point at which MATLAB's documentation had a mathematical typo in it, which they may have since corrected. But the algorithm is good. And it doesn't affect this particular thing, but some further reading. And you do that, you do an FFT of something, and then you're gonna make yourself an axis where you tell it how long your signal was to begin with, and then you know what the sampling rate is. And I always recommend doing that. And that completes the machinery for your last problem set / project, because it could take longer and you may do more. And then we have one more lecture to do the spectral stuff, which is squeezing it all in there. And then really, I might want to give one more lecture that maybe I'll just talk into the camera and record it.